In our CPU, we've got two places where we can store information, in the registers and in the memory. And we want to be able to put information into registers and put information into the memory. And we've seen how we can do that with literal numbers using the data command. Now we also want to be able to get the information from the registers and put it into the memory. And we want to get the information from the memory and take it back to the registers. So we're really looking for register to memory transfer and memory to register transfer. And we're going to use another couple of commands called the load and store commands in order to do that. So let's get cracking with this one. Now I've already set up a file and it's called ctm_memory.asm. Okay, so remember ctm is code the machine. Now another thing is that every so often I will actually look to my side, because the screen I'm actually working on is the other side here and it's a bit easier for me to see on it. So we're going to start off with origin 0x8000. Now let's say we had something like we've seen in the previous video that we had something called an assembler directive, and this directive was called EQU. So EQU stands for equals or equate. So I actually prefer equate. So let's say we have fish underscore chips 0x8500. Okay, so we know that this 0x8500 is a memory location, because if it was a number it would have the hash in front of it. So we know this fish and chips refers to a memory location. Now let's say we had the other directive, and this one was cost, and cost was hash 5. Okay, so we know that the cost is an actual number. Okay, so it's hash 5. If you like, we can say fish and chips cost £5. Okay, now these are what we termed directives, because these are bits of information that we give to the assembler. So there's not going to be, it's not a command in the sense that it has an actual number associated with it that goes into a memory location. Okay, so it's not in effect part of the machine code that gets loaded into the machine. It's simply a directive to the assembler to tell it to do something for us. Okay, that's why it's called an assembler directive, or you sometimes hear pre-processing directives, if I remember correctly. So given we have this here, we could do something along the line of we could say data, and we could put cost into fish underscore chips, and we could put end. Okay, so we know the data command is going to put a number into a memory location. So the cost is the number 5 and the memory location is 8x500. Okay, so let's just terminal run and we'll see that actually running. So that's it assembled, and I'll go simulate, I'll reset this so it's ready to go. So that's it all ready to go. We'll drop down in, edit, open. It's already pointing to the file here. Open this, close the window, design, user panel, simulate, tick enabled. So that's it ran through the simulation. We know it's finished because the 85800 here and the little red light is on. So simulate, we'll stop the simulation. Now if this has worked, it should have gone to a location 8500, which in effect is fish and chips. And if we find this 8500, and it should have put the number 5 in. So there you go there. So if you like, this is one method we have, but it's not really the method we're going to use, but it's one method we have of, in effect, kind of declaring a variable. We could say that fish underscore chips, which is a memory location, is the variable. So in effect, when we deal with variables, what a variable means is the address of a memory location. In this instance, it's 8500. Now, the contents of the address there in this instance is going to be a value of 5. But of course, we could change the contents to anything. We could change it to 7, 9, 12, whatever. But it doesn't matter. The variable still remains the same, meaning the memory location remains the same, but the contents can change. That's what a variable is. So that's one way of declaring a variable, but when we look at other directives in the next few videos, we will see that that's not really how we're going to use the EQU value. We're actually going to use the EQU as a constant. So in effect, it kind of defines a constant value that doesn't change. For example, the number pi, okay, or the number e with 2.718. But we can use it like this, and we can think about it in terms of defining a variable. Now, if we want to get access to, for example, if we want now to be able to take the information from the memory location and bring it back into the register. So this is a memory to register transfer. We're going to use the load command. So load is loading from memory to a register. Now we're going to remember that whenever we do it, it's the command and it's going to be the source then destination. So the source here is the memory location. That's where the value comes from. So in this case, the memory location is going to be fish underscore chips. Okay, now the next one is the destination. So the destination here is always going to be a register. So what register we're going to put it in? Well, we could put it in register R0. Okay, and then we can put the end. So the thing that we have to understand here is that whenever we use the load in the store, the load in the store will only work on the contents of the memory locations or the contents of the register. So for example, whenever I put in load fish and chips into R0, it's actually going to load the contents of the memory location fish and chips. So it's going to load the value of 5 into this register R0. It's not going to load the number 0 cross 8500, which is the position in memory. It's actually always going to load the contents of the memory location. Okay, so that's the same for the load and the store. So we can't get access, if you like, to the variable fish and chips, which is 0 cross 8500. Okay, we can only actually ever get access to the contents, okay, using the load and the store. And I'll show you in a minute how we can get access to the 0 cross 8500. So that's going to load fish and chips into R0. Okay, now if we wanted to, we could take the value fish and chips, which this instance was the number 5, and we can store it back into memory. Okay, so we can store, now again it goes the command and then the source to the destination. So what do we want to store? We want to store the contents, say, of register R0, which we know is going to be 5, and we could store it back in fish and chips. Okay, so it would store it back in the same memory location. But of course, we won't actually see anything happening, so I'll just put in the next memory location along. So if I put in 0 cross 8501, then it's going to take the 5 and it'll put it into the next memory location. Okay, so we'll get a 5 and a 5. So let's just quickly see that this actually does work. So we'll terminal run task, assemble file. So that's assembled successfully. And simulate, we'll reset the simulation here and here, drop down in, edit contents, open, open, close, design, user panel, simulate, tick enabled. And you see that's it finished. And we've seen that the first part here was load fish and chips into R0, so it puts the number 5 into R0. We'll stop the simulation. Now it should then store that content of register R0, which is a 5, into the next memory location along. So let's get in and we'll have a look and see. And we go to 8500, and there you can see, so that's where it has put in the original data, cost, fish and chips. So put the 5 into fish and chips, and then down here is where it's stored the contents of register R0 into this memory location, which is 8501. So that's how we can move information from register to memory and memory to register. Now, the thing that I mentioned was that what if you don't want access to the actual contents of a variable? What if you want access to the variable? I mean, the variable means the memory location. Well, we can't use our data command for it. We can't use our load and store command. Now, potentially I could have designed it from the start differently, okay, where we could have potentially used load and store commands, and we could potentially still add in a command that would potentially be able to use it, okay, but we're not going to do that for the moment. We're going to, the structure of the command is kind of quite well fixed, and it works quite well because I have written thousands of lines of code and it's a-okay. So what we're going to do is we're going to introduce another idea, and this is probably the main idea of the video actually, and that is the stack. So it's probably best for me just to actually work through the example and see the stack working, and then it'll become obvious what it is when you actually see it. So we've got two commands for this thing called the stack. Now, one of the commands is push, and it pushes values onto the stack. Okay, so we can push a value onto the stack, and then we can push another value onto the stack, and it puts the next memory location, that chooses the next memory location and puts a value in. And then we can push another value onto the stack, and another one, and another one, and we can create a stack of values, okay, by using the push command. Now, the other command is the pop command, and it pops values off of the stack, but it's going to pop them off. If we put it in for the bottom all the way up, it's going to pop them off from the top all the way down. Okay, so if you want, it's going to be a case of the last in is the first one out. So say that again, you can see it's going to push them all in here, and the last one that comes in will be the first one that gets popped out, and then the next one that gets popped out is the next one down, the next one down. So it's last in, first out. So let's have a little look, and we'll see how we're going to get access to the variable and the value of the variable. So I could put in push fish underscore chips, right? So that's one push that I could do. Now the other push I can do is I could say push, and in brackets I could put fish underscore chips. Now, whenever I say push fish underscore chips, it is going to push the actual variable, meaning it's going to push the value 0x8500 onto the stack. So that is a memory location, and it defines the variable. And that's how we're going to get access to the actual variable. Now, the other one here in the brackets really says push the contents of the memory location onto the stack. So the contents in this case is the number 5. So this is the way we're going to use it so that we can get access to a variable and the actual value held in a variable. And we can't do that using the data. We can't do it using the load, and we can't do it using the store. This is the method that we're going to use within our assembly language. So if I wanted to, I could put in here, pop the value off. So I could push fish and chips, which is 0x8500, onto the stack, and I could pop it off and put it anywhere. So I could pop it off and say, let's pop it off and put it in register R0. Okay, and then I could push that one on the stack, and I could pop it off into register R1. Okay, so let's just run this now. Simulate, run, assemble, and you see assembly successful, which is good. And we'll go simulate, reset, reset. We'll drop back in, edit, open, open, close, design user panel, simulate, tick enabled. Now an interesting thing to see here, I'd never actually put in the end command here, so I'll stop this, simulate, I'll reset it, and I'll put in the end command so that we can make sure everything runs okay. End, I don't like it whenever I don't finish it off properly. So assemble file, and we'll drop in here, edit, open, design, user panel, simulate, tick enabled. Now it should end properly. So you see that's it ended. Now you may have noted, but it was quite quick. The stack pointer, you'll see here, it actually starts counting. It counts down and then counts back up. So it starts off at F0, and then it changes to a different value and another value, and then it drops back down again to F0 again. But let's go in here, and we notice that we've got the actual variable name, variable location, which is 8500, and we've got the contents of the variable, which is the value of 5. Okay, so that's how we can get access to these. Now you have to be careful about the stack, because you have to make sure you push and you pop things on in the correct order. So I've got 3 books here as an example. So let's say that's book 1 that goes onto the stack, and then you'll have, for example, book 2 on the stack, and then you have book 3 on the stack. Now if I want to get access to book 1 at the bottom here, well, I can pop the value off the stack, but if I pop it off, I've popped this one, you've got the wrong one. You'd have to pop again, and now you pop this one, you've still got the wrong one. So you'd have to pop it again, and now you've got this one, which is the correct one. So as a programmer, you have to take care of the stack. You have to know what values are at the top of the stack, and you have to know how to get access to whatever value it is that you want on the stack. So this is a thing peculiar to assembly language programming. Maybe at high level language programming you don't have these complexities. So that said, let's clear this off, simulate, reset, and I'll just show you that in operation. So if I was to say, for example, we popped these off in that order, okay, now if I changed this and I had something like pop R0, then pop R1, then it's going to first of all pop off this value here, which is the value 5. So 5 will get into register R0, and then the value of 8x500 will get into register R1. So this is the opposite way around from what we've seen whenever we put the pop in here and the pop in here. Okay, so we're going to get it popping off differently. So we'll just see this actually running again. Run, assemble, and we'll load this up. Edit, open, and we'll go back up to the top level. Right, simulate, tick enabled, And you can see that they're round the other way now. We've got the 5 in here and the 8500. Okay, and that's just because it's a last in, first out. Whenever we push the values onto the stack, the very last one that goes onto the stack is the first one that gets popped off. And you have to make sure that you maintain that and understand what is on the stack at any particular point in time. So it's quite a complicated video, I think, now that I've come to do it, but we have covered quite a lot. So the main points I want to take away for this are that the data command can be used to put literal numbers into the registers or into the memory. The load command is used to get the contents of memory locations into the register, and the store command is to take the contents of a register and put it into memory. And the load and store will only act on the actual contents of memory locations. It's not going to work on the actual memory location itself. Now, if you want access to the memory location, or if you like the variable, the best and the simplest way to do it is to use the stack, and you can push values onto the stack and you can pop the values back off. So that's really enough for this video. It's going on long enough now. We will be using the stack an awful lot. It's really useful for us, and at some point I will go through and I'll show you the circuitry that we use in order for us to generate the stack. And you can see if we drop into the CPU, we've got some things a little bit small, but there's one over here called SP, which is stack pointer, okay? And that's what we're going to use in order to point to the particular position within the stack. So that's all for this video. As again, I'm unsure what I'm going to do in the next video. I just kind of have a little think that morning. I think what would be an interesting thing for us to look at. So maybe the next video I might just go over a list of all of our instructions, because we went through quite a few so far, maybe 10 or 15 so far, and there's 81 in total. So if you look at all the rest of the instructions, it will give you a sense of what you've still to do. Okay, so thank you for listening. I'll get you on the next video. Goodbye.